All right, so I'm Jeff Law, VP of Software for Ventana Microsystems. Don't let the VP fool you. I actually write code for a living. I look at assembly code for a living. So we'll touch on state of performance analysis for RISC-V, talk about a few examples of branch mispredictions we're finding with using more modern performance analysis tools, unprofitable vectorization cases, a couple of caveats we need to be aware of on the microarchitectural space. And I don't know if we'll get to it. We are kind of short on time, but avoiding bad speculation is an interesting problem as well. So when I was here 2 years ago, there were no vector designs that you could get. So we were stuck with looking at things like instruction counts or looking at instruction mixes and using that in combination with our experience in the field to understand where performance likely was. But we didn't have any way to actually measure real performance. And for those of you who have worked in this space, you know that instruction counts work reasonably well in a scalar space. But once you get into vector and more complicated operations, counting instructions can lead you wildly astray. So what's changed? RISC-V hardware is available. You can go out and get one on Amazon that runs RISC-V vector. It is capable enough to run Linux. It's capable enough to run Linux perf. In addition to actual boards being available, we know that there are companies that do have silicon in-house now that is capable of running Linux and Linux perf. And there are FPGAs. I think there's a number of companies that have FPGAs that they can gather performance data on. And really what we want to be doing is looking at the performance monitoring unit to do sampling. That is really the biggest change in this ecosystem in terms of performance work. So PMU sampling, it gives us insight into both performance as a whole, but also performance at almost all the way down to the instruction level. So in one mode, you can ask perf, how many cycles did this run of a benchmark take? How many branch mispredicts did you get across this benchmark? That's one mode. Interesting. But from a compiler development, what I really want to know is where things happen. And this is not exactly how Linux perf works, but it's a good mental model. Is you can essentially say, I want to get an event every, let's say 2 million branch misses. I'll get an event, I can record data at that event, and from that data, if my benchmark runs long enough, I can build a very accurate statistical model of where that event was occurring at the source or at the binary level. And that allows us to go in and do a deep dive and try to understand, is there something the compiler ought to be doing to make code perform better? Last but not least, Linux perf is standard. So if anybody's doing optimization work, they should have a basic understanding of perf. So as we as a group move into the perf space, that's going to enable others in the Linux space to help as well. All right, so let's talk about branch mispredictions. So modern branch predictors are amazing. I love them. They make my life a lot better. But in modern architectures, it's not uncommon when you have a branch mispredict. The penalty for that mispredict is going up. The deeper your pipeline, the more things you have to unwind. And what we found is focusing on mispredicted branches is important, but you got to make sure you focus on the right branches. Just converting a branch in and of itself is not useful. It really needs to be something mispredicted. If the branch predictors are able to lock on a pattern, it's as fast as any other code without branches. So I happen to be looking at GCC input 2 from spec 2017. I don't remember why, but I saw an interesting quirk. The top 2 functions in terms of cycles also happen to be the top 2 functions in terms of branch mispredicts. So what was going on? So this is compute trans-P. It's a part of GCC's global CSE algorithm. I actually wrote this, I think, in '98. And this is about 26% of branch mispredicts in compute trans-P, which is the hottest function, come from that little blob of code. And I've showed the entire loop, and as well as the fall-through path, which is where most of these branch mispredicts are happening. But what's really interesting here, has anybody figured out what this loop does? It's just count trailing zeros. We didn't use the CTZ instruction. The question is why? We didn't use CTZ because in the source form, if the input value is 0, which can't actually happen, but the compiler can't prove it in the original source form, if the input value is 0, it loops forever. And so the optimizer said, I don't know what to do with that. I'm going to take a conservative approach and leave it alone. And really all we need to do is precondition loop from the compiler standpoint. So that whole loop goes away, turns into a CTZ. So that's about 1/4 to 0.5%. That sounds really small. Improving by 1/4%, it doesn't make you wake up and go, woohoo! But given where we are with GCC's performance, that is the state of things I'm looking for. We are incredibly happy with where GCC is performing right now. We have an internal target for our customer. We're at about 1 to 1.5% off that target. So finding quarters and halves, that's where I am. Another example, this is from bitmap setbit. Same idiom appears in bitmap clearbit. And this is something Intel actually found maybe 6 to 9 months ago upstream in GCC, but nobody looked at it from a spec standpoint. So what we have here is we're loading a chunk of memory. We're gonna test 1 bit. So A7, just take it on my word, it's 1 bit set. If the bit is not equal to 0, then you go on the one path. The path where we fall through has a huge number of branch mispredicts. And if you look at it for a minute, we have a load, we have a store to the same memory location. All we do is flip that 1 bit back on. So we could just wipe the branch out, do the store automatically after turning the bit on, and we have this one little load immediate in here. We'll have to adjust for that, but this is pretty straightforward conceptually. I've got an engineer working on this. Intel's data says this is about 1%. Not huge, but again, I'm fighting for nickels and dimes at this point. Unprofitable vectorization. So, in the right circumstances, vectorization could be hugely profitable, a factor of 2 in aggregate across something like x264. But you have to be really careful that you don't end up with a mismatch architecture. So if you have the ability to do 4 scalar integer operations per cycle, and you're only looking at a 4-wide vector, it's hard to be profitable in that space. And we've seen that in sub-DCT out of spec. That's part of the x264 benchmark, and it's a 4-element chunk of code doing a subtraction with some kind of transform in the middle. So that's where it sits on the profile right now. It's about 5% of the runtime. And just so you know, Pixel SATD, this is from LLVM. I have engineers working on that. That's a much more interesting problem, but it's we know how to solve it. It's already been solved. It's strides. If you do strides right, that goes away. GetRef is pixel average. So you do a good pixel average, that goes away. And since I already have engineers that know how to fix that, I started looking at sub-DCT. Sub-DCT, interestingly enough, is using index loads. Who here has looked at index load performance? I know you have. Index load performance on every architecture I've ever worked on is not great. And if you have an index load, you're probably doing something wrong. And this is, 90-something% of the time in sub-4 DCT is index loads. But it's really hiding the bigger problem, and that is that you have to have a good cost model. What we found working on our design is you need to integrate the costing model for index loads, segmented loads, strided loads, all as a first-class citizen in the vectorizer. If you fail to do that, you're constantly trying to second guess what the back end's gonna do. So you've got to make sure you cost this stuff correctly. And you also have to include the costing relative to your scalar ALUs. That's a few percent on x264. Microarchitectural quirks. So RVV has a lot of really interesting instructions in the vector side. The one I find kind of the most interesting right now is the zero-strided load. So in RISC-V vectors, you can have a load of a chunk of memory and then a skip, which is your stride, another chunk of memory, another skip. The skips have the same amount of data skipped. So that's a strided load. The skip shows up as a register. You can use register X0, which is hardwired to 0. And the ISA says the design is allowed to only read that memory location once in a stride 0 case. So you can save a lot of memory reads, and it splats that value across the vector. I've worked on 2 architectures that are supposed to handle this reasonably well. But guess what? It's no faster than just doing a standard load and a standard vector broadcast. So essentially, we can't use this. We don't want to use this right now because it does not perform. There's an example in B-Waves. There's about 6 of these, maybe 7, in a hot loop in B-Waves. So it takes that floating point load and the vector broadcast, turns into that zero-strided load idiom. It reduces the instruction count by about 5%, but makes everything run about 5% slower. on 2 different microarchitectures I've looked at. So we really don't want to be using this. Speculation. So bad speculation is an interesting problem. So Ventana's design has a fetch block-based optimizer. So you guys are probably familiar with Fusion, where you're looking at pairs of instructions in a decoder. You have, and your ability to do much more than pairwise fusion is very limited because you just don't have a lot of time since you're in the decoder phase. So what we have is an offline fetch block optimizer. Once the processor's decided a particular chunk of code is hot, it puts it in a cache, and then it optimizes that cache into internal instructions. Now, vset-VL is somewhat problematical in that space. Once a vset-VL gets into a block, it doesn't go through that path. So we lose the ability to optimize the block with our offline optimizer. And then we've also seen, kind of in combination, we've seen some designs that very much want to remove vset-VLs. And so they tweaked the lazy code motion algorithms in such a way that it removed one of the cost model constraints that has been in there since the 90s. I know because I wrote it. And we've known for a long time that that cost model constraint, relaxing it can significantly improve certain codes and loops. So I understand why they did it, but we have to be careful here. So in sregmatch, which is from Perlbench in Spec 2017, we have this really fantastically big basic block. It has about 33 instructions in it. And we end up bringing that vset VLI into the middle of a 30 instruction block. Prevented optimization of the block, and then also prevented us from using the additional bandwidth we have from that unit into our execution system. So we took 2 hits there, it's about 1%. The good news is fixing that is easy. The other one, and I don't have a design that has this particular quirk, but I'm aware of at least 2 designs where when you set VLEN to 0, performance falls off a cliff. So how can that happen? Well, one, the case I just showed you where we speculated vset VL out of cold code into hot code, that could potentially set a VLEN to 0. It can happen if the compiler speculates a vset VL out of a loop, and that loop only enters if the vector length was going to be more than 1. So we now have tuning knobs in GCC to allow us to say, this microarchitecture does not want VLEN ever set to 0. So do not speculate vset VL instructions ever. I don't know what the performance gain from that is, because again, that's not designs that I have direct access to. So that was actually the stuff I want to talk about. So we're at a little over 10 minutes, so questions. And I won't direct them to the Ventana booth that doesn't exist.
Yeah, to address some of these challenges, we don't want to have every machine having lots of quirks, and we'll never get a performant portable. So there's these optimization guidance options coming through that'll pin ISA strings as big O something. In particular, a few of these things, once people see, oh, that's the requirement, they'll then have to go fix their implementation to follow because otherwise you end up having to write suboptimal code for some other implementation that kind of did it right. So to raise the bar, especially in the RVA space, we're going to be putting these in. So the expectation is in the future,
yes,
future profiles, they will be mandated that your behavior looks like, oh, you should be expecting software will expect this. This is one example. Another one is hardware misaligned loads.
There's many, and that is the exact topic that we had a really long discussion about at the GNU Cauldron last month, is when do you tune it to say, like index loads, for example. I haven't seen a design where index loads actually ever improve performance. That's one we might kind of steer away from. Something like the zero stride load idiom. I would expect next generation designs to probably fix some of those problems. And so we want to make sure that when we make recommendations for distros about how to generate code, we want to find that sweet spot and not worry quite as much about these quirks. These quirks are in many ways a benchmarking artifact. We have the distros to generate generic, good performing code.
Yeah, I just say we want to actually formalize this in these guidance options so people understand this is what's expected.
Yep, and I know that Greg is working with you guys to try and figure out what language to use there. It's not trivial. Other questions? Yeah.
So following what you
I could give you my mic, but you project quite well, actually.
Yeah, you related to what you answered in the previous question. You said you didn't see much improvement on the zero-strided load or any improvement. Therefore, you're not recommending it. But that seems counterproductive because it's something that can be optimized later. Whereas well, I guess you could do the fusion of the load and the broadcast. But it seems that if something is not worse, you should still use it.
It is actively worse.
Oh, it was worse?
It's about 5%.
Oh, it was worse. Okay,
Yeah.
I didn't get that.
So it's
All right.
about a 5% improvement in instruction count, but a 5% increase in cycles.
Okay.
But it does very much touch into that other question is, should we steer away from that? Right now, it's microarchitectural only. That's when we steer away. And the distros will never flip a microarchitectural flag. I spent 20-something years in the distro space. What they want is generic tuning. So distros will still get a zero-strided load.
Okay.
And if it doesn't perform on a design that goes out in the wild, that will show up, and there will be pressure on the designers to go fix it.
So distros are not optimized for each microarchitecture? Is that what you're saying?
The distros are not optimized per microarchitecture.
Oh, okay. Thank you.
Yeah, they really, it's a QA problem, right? Because if they start tuning for a particular microarchitecture, it changes the code, and doubles or triples or quadruples, they're a QA problem. I lived in that world. I have sympathy for them.
Thank you.
Yeah, no problem. Other questions? All the way in the back.
Hello. You talked about issues with speculating and fetching and fusing across VSETs. Is this only with the indirect forms of VSET or including more direct ones?
What do you mean by indirect form?
Where you're setting it from a register, either V-type or VL versus the immediate.
Yeah, it's always when you're setting it to a register.
Okay.
Yeah, always. Because if it's an immediate, you know you don't have to do that one. It's setting a type. It's a type pun. Other questions? Or if we're out of time?
Yeah, the last one.
Last one, if there is one?
No questions?
I guess not.
No.
Thank you very much.
Thank you, Jeff.